Okay, let's get started. So last time we were in the middle of talking about something called, one second. We were in the middle of talking about something called Rolle's theorem. Remember, Rolle's theorem was a theorem which had three hypotheses and one conclusion. So if f is continuous on the closed interval AB, secondly, f is differentiable. When you see differentiable, think smooth. On the open interval AB like that, and f of B equals f of A. Those are our three hypotheses, and our conclusion is there exists an x value C somewhere between A and B such that the derivative of C is 0. And we took a look at a picture of that last time to see why that should be true. So we have these two x values, A and B. According to hypothesis 3, the curve is at the same height at these two endpoints. So whatever height we're at height A, at x equals A, we're at the same height once we get over here. This dotted line is not part of the curve. I'm just drawing that so I could put those 2 points at the same height. And one says I could start at this point and end at this point without picking my chalk up from the page. And 2 says, not only can I do that, but the curve is nice and smooth. Now, the reason we say it's differentiable on the open interval, if you think about the definition of derivative, remember that it's a limit. I can't even define the derivative at these two endpoints. I don't even know if the function exists to the left of A or to the right of B. So I'm restricted to saying it's differentiable, it's smooth between the endpoints, not at the endpoints. But it goes up, maybe it goes down, who knows? But at least at one point, somewhere between A and B, I could pick that point on my picture, or I could pick this point. There's a place where the tangent line is horizontal. Okay, so let's talk about the idea of the proof. The proof is sort of written out formally in your textbook if you look in the section that has to do with Rolle's theorem and the mean value theorem, that's section 3.2. I'm just going to give you the idea. This is a proof by cases. So you've probably done a proof by cases when you were back in high school in geometry, where maybe you were doing something about triangles and you prove it for an acute angle triangle and an obtuse angle triangle and a right angle triangle. You do those proofs separately because a triangle's got to be one of those. It's the same with this. At least one of three things has to be true. So at least one of three things must be true. The first thing that might be true about the curve, let me say about f of x between x equals a and x equals b. First thing that might be true, maybe I shouldn't use 1, I use a. First that might be true is it could be that the curve is just a horizontal line between a and b. So y equals f of x could just be a horizontal line between x equals a and x equals b. That's certainly consistent with all three of these hypotheses. If that were true, then f of b would be f of a, it'd be at the same height at the endpoints, and the curve would be nice and continuous between a and b, and it would be nice and smooth. If it was just a horizontal line, all three of these things would be true. If that's the case, just let C be any point between A and B. If it's a horizontal line, then any point between A and B has tangent line that's a tangent line that's horizontal, derivative equals 0. They're all perfectly nice candidates. Just let C be any x value between A and B. Okay, maybe it's not a horizontal line. If it's not a horizontal line, it either has to go, the curve either has to go above this height at some point or below this height at some point, or possibly both. In my picture, the one I've just drawn right now, it goes both above and below. But if it goes above, if part of y equals f of x is above height f of a and f of b are the same height. This is both f of a and f of b. We said they were the same height. If part of the curve goes above that, then we have a nice smooth curve, nice smooth continuous curve, and we know it has a maximum. Then by the extreme value theorem, f has a maximum on the interval a, b. And since we assumed it went above this height, that maximum can't be at the endpoints. The highest point, if it goes above that height, maximum be at x equals a or x equals b. If it goes above this height, then the highest point's got to be above that height. It can't be at the endpoints. The endpoints are down here. If it goes above the height, it's got to be somewhere in the middle. So we already know that at maximums, at relative maxima or minima, we're at a critical point. So say the maximum occurs at x equals c, then we know that x equals c, so c is certainly between b, and we know that x equals c is a critical point. We know that maxima and minima always occur at critical points. We talked about that theorem last time. It's a critical value. So it's somewhere in between here. It's a critical value. It's a critical point. We know critical points are places where the derivative either equals 0 or it doesn't exist. But hypothesis 2 says it definitely exists, so it's got to be 0. So since f is differentiable, on the open interval AB, f prime of c must equal 0. So if it goes above this height, there's a highest place, it's a critical point, which means either the derivative equals 0 or it doesn't exist, but it definitely exists because of hypothesis 2, so the derivative has to be 0 there. And lastly, hang on, somebody erase my line on the board where I can see where the edge of the board is. So either it's a horizontal line, it goes above this height, or it goes below this height. 2 and 3, B and C could both be true. So if part of the curve part of y equals f of x is below f of a, just repeat argument B, except where I said maximum, replace it with minimum. Repeat argument B, except replace maximum with minimum. Wasn't sure we could switch this whole proof onto one blackboard, but looks like we more or less did it. Yeah, I've written this out slightly informally. If you're looking through your textbook for the proof of Rolle's theorem, let's see, you will find it on page 172. It's written out a little bit more formally there, but you'll find that what they wrote there, if you're curious, is basically what we wrote here. It's the same idea, just with more symbols. So I'm going to call this some kind of proof. I mean, it's a little informal, but I'll call this proof. At the end of a proof, to indicate the proof is finished, we usually put a filled in square. That tells our reader that the proof is all done. So you usually write the word proof at the beginning. It's a little informal, so I wrote idea of proof. At the end of a proof, you put a filled in square. Okay.
What does the word after repeat say?
Oh, repeat argument B. So repeat
Okay.
this, so argument.
Okay, thank you.
No, no problem. Except replace maximum with minimum. Yeah, I again, if you were all here, I'd have a lot more Blackboard to work with, but we're a little bit pinched for space, and I wanted to be able to have the theorem and the proof on the Blackboard at the same time, which meant that I sort of had to squeeze things in. So sorry. Okay. I am going to start erasing this. I want to leave Rolle's theorem up on the blackboard, the statement of Rolle's theorem, and hopefully I can erase this column too. Leave C up for a second in case you're still finishing. I guess the recording will all be up later, and so you can double check things from the recording. So I want to jump right in. So Rolle's theorem, basically, in a sense, we never use. Rolle's theorem, the only thing we use it for is to prove the next theorem. It's called the mean value theorem. The third theorem that ends value theorem. We've seen the intermediate value theorem, the extreme value theorem, and now the mean value theorem. And I know this is not going to come as a huge shock, but we abbreviate this MVT. And I want to put this right next to Rolle's theorem for a reason which will be obvious in just a second. So if f is continuous, on the closed interval AB, that should look familiar. And f is differentiable on the open interval AB like that. So far that should look exactly like Rolle's theorem. But we're going to leave out hypothesis 3. Then, so this time, there's no demand that if here we are at x equals a and here we are at x equals b, that we're at the same height. Of course, this is f of a. And this is f of b. This one could be higher than the first one. It could be lower. It doesn't say. Now to see what our conclusion is. Obviously, or maybe obviously, it can't be the same. It's totally possible to draw a nice smooth curve between here where the derivative is never 0. If we don't end up at the same height at the two endpoints, there's no reason that there's any place between A and B where the tangent line is horizontal. So we can't possibly have the same conclusion. Let me tell you what the conclusion is in the mean value theorem, and then we'll see if we can figure out why it's intuitively clear and what it means. So then there exists an x value C in somewhere between A and B, such that f prime of C equals, so far it looks the same, but we know it can't be 0 there. That doesn't make any sense. It's certainly not a true statement. F prime of C equals f of B minus f of A over B minus A. So if I'm looking at this for the first time and I'm comparing Rolle's theorem with the mean value theorem, I'm going, okay, well, the set of hypotheses looks easier over here. There's one fewer of them. I don't have to worry about this, which is a little bit artificial, keeping the height at the endpoints, the same. Why should that be true? But the conclusion looks more complicated. Here the derivative equals 0, horizontal tangent line. Here the derivative equals, I don't know, f of b minus f of a over b minus a. Now some of you might be looking at that and going, oh, I know what that is. I would have known what that was long before I ever walked into a calculus class. This is something that should look very familiar to you from like algebra. So let's go ahead, let me draw a curve. Your curve can look different, but what I want is to draw a nice smooth curve with no breaks between these two endpoints. Mine's gonna look like this. I'll do something like that. Yours could look different. As long as it starts here and ends here, and I don't know where you put your points. You might have put this one below this one. I don't know. But as long as it starts at one of the points you drew and ends at one of the points you drew and is nice and smooth, then you're good. Okay, f of b minus f of a over b minus a. Well, b minus a is just this distance here. And f of b minus f of a is just this distance here. So this is f of b minus f of a. That's that distance. And this, of course, right here is b minus a. That's that distance right here. And when you think of it that way, what you have here is rise over run. This is nothing more than the slope between these 2 points. So the slope of that line is f of b minus f of a over b minus a. Slope, that's a concept you learned way back in Algebra 1, and we reviewed at the beginning of this course. So all this theorem says is that there is some place, at least one place, between x equals a and x equals b, where the tangent line to the curve has the same slope as that line which connects the endpoints. So in my picture, it looks like it's about here. And there might be more than one, but there's at least one, where the tangent line to the curve, the line which just grazes the curve, is parallel to the line which connects the endpoints. So my c is the x value where it happens. And there could be more than one possible c, just like in the previous example. But there's at least one place between the endpoints where the tangent line is parallel to the line which connects the endpoints of the curve. Let me give you the idea of the proof of the mean value theorem. What you do is give an f. So here we have our curve y equals f of x. So given your f, form a new function g. Form a new function g by taking g of x to be f of x minus this slope, f of b minus f of a over b minus a times x. Let me put this in parentheses, that slope. It's just a number. F of b minus f of a over b minus a. There's no x's in that. That's just a number. So it's just in this case, it's just a slope. And let me draw you a picture of what happens. if you start off with a curve, here's A, here's B, and the curves are at different heights between them. Let's say the curve looks like that. And you subtract, so if this is y equals f of x, and you subtract off that, which is just a number times x, it's just a line through the origin, what you end up with is another curve, which looks a lot like this curve, but it's shifted. We sort of subtracted off the line which connects these endpoints, and we end up with something that looks like this. And the important part is that these two values are now at the same height. Once you subtract off the line, which basically, controls how much the curve grows between the beginning and the end, then the beginning and the end are now at the same height. So now you apply Rolle's theorem to G. So you apply Rolle's theorem to G. So there's some x value C whatever. You apply Rolle's theorem to G, and you know that there's some place on G by Rolle's theorem where the tangent line is horizontal. Now, if you go back to f at that same x value C, you'll find that at that x value, the tangent line is parallel to the line which connects the endpoints of f. So apply Rolle's theorem to G to find x equals C. And the same C works for f. Same C works for f. That, again, is pretty informal, but that's the idea of the proof. And if you go ahead and look at the proof, written out on all its splendor, which takes a little bit more work, on page 174, you'll find basically that's what they did. So I'm going to put a little box at the end of here. Okay, so before we move on, I want to call a few things to your attention. So if you look back at the proof of Rolle's theorem that we did, you'll see that we used the extreme value theorem to prove Rolle's theorem. That little arrow sometimes means implies, so we used the extreme value theorem to prove Rolle's theorem. And we used Rolle's theorem to prove the mean value theorem. If you go back in your notes and look at the class we did on the extreme value theorem, we didn't prove it together. I didn't prove it for you. If you look in your textbook, you will find no proof. That's not because we're trying to keep secrets from you. I promise you it's not. The proof of the extreme value theorem requires mathematics, which is sort of beyond the scope of this course. We'd need an understanding of the real numbers, which we just don't have yet, and would take several months to develop. So it's just as important to know what we don't know yet as it is to know what we do know. So I want you to realize that we really don't know how to prove the extreme value theorem. When I say we, I mean in this class at this level. It can be proven. And for those of you that are interested in mathematics enough to keep going on, we have a course in the 4th year of mathematics and at the senior level called analysis, and we do prove it there. But it requires a lot more mathematical machinery than we are sort of ready for right now. I also want you to be aware that if you look back in the your notes where we did the intermediate value theorem, I didn't give you a proof of that either. And it's for the same reason. To be able to do the proof of that, to be able to demonstrate why it's true, we need machinery that we don't have yet. So if you imagine that we're sort of building a building, the mean value theorem sort of as a floor rests on like this floor. Like if this is like the 3rd story, this is the 2nd story, and this is the 1st story, but we actually don't know what's holding the 1st story up. And we don't know what's holding this up either. If that bothers you a little bit, if you're the sort of person who likes to know what you know and why it's true, me too. It bothered me until I knew the proof and until I knew why it was true. And then once I knew why it was true, I saw why I didn't do it in Calculus 1. It was clear to me that it just required a lot more mathematical understanding than I had in Calculus 1. But it's just as important to know what we don't know as it is to know what we do know. But we were able to take the extreme value theorem and use it to prove rolls. If you look back at the proof of rolls, you'll see that we used the extreme value theorem. And clearly we used the Rolls theorem to prove the mean value theorem. Okay, so remember that. I remember an epiphany that I had as an undergraduate when I was taking Calculus 1. How are we doing for time? Oh, good. Where it finally occurred to me what the purpose of the mean value theorem is. And we're about to see what the mean value theorem is good for, at least in one case. But let me just sort of spell it out for you. The mean value theorem is important if you know something about the derivative, it tells you something about the original function. Up till now, we have been doing things in the opposite order. If you know the original function, then you can tell me what the derivative is. We spent a lot of time learning derivative rules, developing derivative rules. You know that if I know position, I can take the derivative and get velocity. If I know the velocity, I can take the derivative and get acceleration, all that stuff. Where you have the original function and you take the derivative. The mean value theorem allows you to know something about the derivative and then make statements about the original function. So let's go ahead and go to section 3.3. Increasing, decreasing functions and the first derivative test. Increasing and decreasing functions in the first derivative test. So this section again begins with a little bit of theory, with first a definition and then a theorem. So let's start with the definition. We're going to talk about what it means for a function to be increasing on an interval. So we say a function f is increasing on the interval a, b if all x values, x1 and x2 in AB, where x2 is on the right and x1 is on the left. If I have two x values and x2 is bigger, that means it's on the right. Then f of x2 is bigger than f of x1, or f of x1 is less than f of x2. So let's sort of unwind that for a second and see what it says. So we have this interval, AB, get a little bit more. Specific about that. So, oh, I guess I should put open circles at the endpoints. I said it was an open interval. So the function's increasing on an interval. If you pick any 2 points in the interval, so here's f of x1, and here's f of x2. If no matter when you pick 2 points, the point on the right is higher than the point on the left. So it doesn't matter which 2 points I pick, the point on the right is always going to be higher than the point on the left. That's what makes this function increasing. Please notice that the definition of increasing does not include the word derivative at all. The word derivative doesn't appear here. If you wanted to sort of write it out in words, you can say, if I pick any 2 points in the interval, the point on the right is higher. It's not just for the endpoints. I can have a function like this. Let me do a closed interval. So if here's x equals a and here's x equals b, the point this point is higher than this point, but it does not mean the function is increasing on this interval, because I can pick 2 points in the middle where the point on the right is lower than the point on the left. So this function is not increasing. It has to work for any pair of points. The point on the right always has to be higher than the point on the left. So likewise, a function f is decreasing on, again, I'll do this for an open interval, but you could do it just as easily for a closed interval, if for all x1 and x2 in AB, where, again, I'll make x2 the point on the right. So x1 is to the left of x2, x2 is to the right of x1. This time, f of x2 is going to be the lower of the two. F of x1 will be the higher of the two. So this time it goes down to the right. If I pick any 2 points, x1 and x2, the y value at the point on the right is lower than the y value at the point on the left. Now notice, I only changed the order of one quality. I left x2, the point on the right, in both of these. I just changed this inequality. If you change them both, then they cancel each other out and you haven't changed anything. Saying that the point on the right is higher than the point on the left is the same as saying the point on the left is lower than the point on the right. So if I change both these inequalities, I haven't changed anything. So if I wrote this, but just change that and change that, I'd be back with exactly this. So that's what increasing and decreasing means. I guarantee on your next midterm, I will ask you for the definition of increasing or decreasing or both. Please don't write anything that, when I ask for the definition, don't have the word derivative or f prime or df dx or anything like that in your answer. It's not part of the definition. The definition of increasing and the definition of decreasing do not include the words derivative. You can write it out in words. You can say, it's increasing if I pick any 2 points, the point on the right has a higher y value. It's decreasing if I pick any 2 points, if the point on the right has a lower y value. That's fine. But don't use the word derivative. Let's see, 7 minutes. So that said, there is a connection, which you may already know or suspect, between derivative and increasing or decreasing. Which actually, I think I'm going to do at the beginning of next class. Are there any questions? All right, I will see you all on Monday.
Thank you.
Have a good weekend.
You too. Have a great weekend.
Dr. Oliver,
Yes.
a small issue with the homework. There's no
Yeah.
submit button on the latest one.
What's that?
There's no submit button.
Oh, that is a problem. Okay, I'll go fix that. Thank you for letting me know.
No problem. Thank you.